Yeah, so hi, I'm Philip. Thanks for your patience. I'm a compiler engineer at Groq, and my talk today will cover the Groq Compiler software stack. I'll touch on the phases of the, yeah, so sorry, yeah, here's the agenda slide. So I'll talk about what is the Groq Compiler. I'll talk about how that fits into Groqflow. From there, I'll talk about the different phases of the compiler, namely the front end, middle end, and back end. And then I'll also focus on two modes available in the back end that give a trade-off between performance and compile time. And from there, I'll talk about multi-chip and how we do multi-chip in the compiler and talk about our intra-op partitioning, and then use transformers as a motivating example. So for those of you who attended the sessions yesterday, you were introduced to Groqflow. It is our recommended way of interfacing with our software stack. The Groq compiler is really the workhorse behind Groqflow. And so Groqflow does some input pre-processing of the original ML graph, and then it calls into the Groq compiler, which takes the ONNX model. So a compiler's job is to take some input program and translate that into the instructions that can run on a target machine. For Intel and AMD CPUs, they compile to x86. For NVIDIA GPUs, it's PTX. And for Groq's LPUs, we compile to Allen assembly. So from here, I'll talk about the front end. So most commonly, an ML program will be written in PyTorch. You express some linear algebra operations you want to execute to do some ML task. And then PyTorch's internal representation of this is some high-level tensor graph. PyTorch has thousands of these operations. G10, on the other hand, has tens of these operations. We rely on PyTorch, or we rely on ONNX to trim down the op space from thousands to hundreds. And from there, our graph intermediate representation G10 takes the ONNX, these hundreds of ONNX operations, and turns them into tens of G10 operations. And so when we talk about a kernel-less compiler, it's the fact that we are only really, we only have specialized codes for these tens of operations. So yeah, let's talk about the middle end. The middle end is what looks most like a conventional compiler, more specifically a SIMDizing compiler. The first part of the middle end is layout marking. Layout marking determines how the tensors in a graph will be tiled and how they'll be mapped to Groq's architecture. With good layout choices, we can reduce the number of shape transformations and operations, and this can easily become a bottleneck because the SXM doesn't have the most throughput relative to the other functional units. The next job of the middle end is to translate these graph operations into instructions that explicitly control the functional units. In the case of matrix multiplication, we would rewrite this into a series of operations that target the MXM, so load weight, install weight, activation, buffer control instructions, and possibly a series of memory reads and writes as well. A transpose might use operations on the switching module, so some shifts and permutes, and more interesting operations might use a combination of instructions from different functional units. So at this stage, we have the what. We know what we want to do. We know the type of functional units we need and what instructions they will call. For most, for a normal CPU, this would be enough and the compiler's job would be done. But we, because of our data flow architecture, we still need to know where to place these instructions on the chip, where the data should live. And so that is where the backend comes in. So the backend's job is really to schedule this compute graph to minimize the number of compute cycles. We have to figure out which compute cycle are we going to place an instruction on, Which functional unit are we going to use? We have multiple MXMs, some in the Eastern Hemisphere, some in the Western Hemisphere. So we have a choice there. What streams are we going to use to route data across the chip? And certain streams are reserved, and that is something that the scheduler has to keep in mind. And similarly, we have to know which memory slices we're going to store the constants and intermediates in. And so we fully expose this to the software. And so we often say our hardware is simple, but as a result, the compiler has to do some more work. So there's two scheduling modes, vector and tensor scheduling. Vector mode schedules a single vector operation at a time, and tensor mode bulk schedules multiple vector operations at the same time so that they can occupy a functional unit in consecutive cycles. These are exposed via the effort flag in the compiler. So if you were to use the high effort, which is the vector scheduling, you may see an improved performance, but at the cost of slower compile times. We're driving down the difference between the performance with the tensor scheduling and the vector scheduling mode. So in not too long, we expect that the tensor scheduling mode will reach parity. But for now, the tensor scheduling mode is the default. However, it is worth keeping in mind that you possibly can change this flag and get different performance on your models. Here's a visual view of the same program compiled with vector scheduling mode and tensor scheduling mode. Just a reminder that this image is a snapshot in time. So this is where data lives on some cycle. So say this is cycle 500. We can see exactly where the data is on the chip. You can see on the left side that there is a lot less regularity. It looks almost random. Whereas on the right side, it is incredibly regular. And this has the added benefit that we can do more instruction compression because of the regularity. And that also increases our chance of being able to fit a model on the chip. So that is another advantage of using the standard effort or tensor scheduling. So let me talk about multi-chip. So on a single chip, we actually have two forms of parallelism. We have SIMD parallelism as the functional units operate on 320 byte vectors at a time. And then secondly, we have multiple functional units which can perform operations concurrently. And this is somewhat analogous to pipelining on a conventional CPU. However, there's another way we can get parallelism, which is by throwing more chips at the problem. So there are two forms of partitioning, intra-op partitioning and inter-op partitioning. For inter-op partitioning, we split the original compute graph into subgraphs, and then we run these different subgraphs on different chips. We pass tensors whose data connects the subgraphs over C2C to the other chips. Similarly, we can split the ops themselves rather than partitioning the model itself. This is called intra-op partitioning. This might be out of necessity as we may not be able to fit the operation on a single chip, or it may be for performance as the operation can be performed more efficiently in parallel. So let's take a look at this in the context of LLMs, and more specifically, the transformer. Now I'm seeing I labeled this FFN in attention, but it should really be FFN in transformers. So most of the compute in a transformer block comes from the feed-forward network and the multi-headed attention layer. I'll focus on the feed-forward network because it illustrates the point, but the ideas hold true for what we do in multi-headed attention as well. So yeah, let's zoom in on the feed-forward network. If we yeah, it consists of two linear layers, one of which is passed through an activation function. The two results are then element-wise multiplied together before a final linear layer. And if we were to put some concrete dimensions, let's give it, let's say the output from the attention is a 1 by 8,192, and the inner dimension of the linear layers is 6,000. I chose those numbers arbitrarily, but we could impose the dimensions of llama 7 billion or another model for what it's worth. From here, what we can do is we can actually split the map moles into so that they can run on multiple chips using intra-op partitioning. So instead of just doing these multiplies with an inner dimension of 6,000, we have an inner dimension of 2,000, and we split the weight matrices into thirds, and we run them across different chips. So a better view of this is this multi-device view. So we have the output from attention. We pass that to device 1 and device 2. It was already on device 0. From there, we run our subgraphs, and here we can cascade the fact that we only have to work on a third of the data. And so each one of these is doing a third of the compute from the original. And at the end, we have a reduce that will reduce the final outputs of the 3 map moles from device 0, device 1, and device 2. And so device 1 and device 2, the map moles there will send that data over to device 0, and that will be reduced together for the final output. So this is very advantageous for allowing us to more performantly do these feed-forward networks, and it's also out of necessity, so we can fit these feed-forward networks. Here I just chose 3 devices as an illustration because that fit better on the slide. So we also get inter-op partitioning with transformers. So transformers are this very linear set of operations. We have a transformer block followed by another transformer block and so on. And so what we can do is we can use 8 chips for 1 or 2 transformer blocks, then use 8 more chips for the next 2 transformer blocks, and 8 more chips for the next transformer blocks, as an example. And this would give us and this is an example of inter-op partitioning. And so effectively, we can combine these two ideas together by using inter-op partitioning on the transformer block level. And inside the transformer block, we have intra-op partitioning. And so using both of those partitioning strategies together, we're able to get some performance and are able to fit LLMs on our architecture. I think that is all for me.